طيب بسم الله الرحمن الرحيم. السلام عليكم.
وعليكم السلام ورحمة الله.
Let's wait for a few seconds before we start. طيب بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome to E21. Before we start, كل عام وانتم بخير وتقبل الله منا ومنكم صالح الأعمال وصلى الله أن يدعي علينا وعليكم بالخير والمسرات. طيب today's lecture will be inshallah a continuation on what we started last time. If you recall, we started talking about discussing chapter 9. And before actually reviewing what we did last time, let me just go ahead and make a few announcements. So the first one is homework 4 is posted, and this inshallah do on Sunday. The quiz 5 will be this Wednesday. The coverage will be chapter 8, basically 8.1 to 8.5. I haven't graded quiz 4 yet, but I will post the grades once they're done. Just let me go over what we did. If you recall, yes, Hadi.
Doctor, 8.5 is not included in the syllabus.
Let me double check. Yes, 8.4. Absolutely. Okay. 8.5 is the outbound. Okay. 8.4. Thank you. Thank you very much. Okay. So if you recall, like during the entire course of this class, what we did was dealing with DC sources that are constant with respect to time. And starting from last time, we kind of like introduced the notion of a source that actually that varies with respect to time. There could be like multiple variations with respect to time, but the most important, I think, is sinusoidal variation, meaning that the source could be a sine or cosine function. If we have a source, if we have a faulted source that looks like this, we have a cosine Vm multiplied by cosine omega t plus phi. We from last time we know that Vm is the amplitude, the maximum value with respect to the maximum value with respect to the center with respect to the mean. Omega t or omega is actually the angular frequency, and omega is given by 2 pi f. F is the cyclic frequency, the frequency that we are all familiar with. Or it could be written like this: 2 pi divided by capital T. T here is the period. Period is the time needed for the sinusoidal function to complete one cycle. And phi is actually the phase or the phase angle. If you recall, also last time we discussed something called the RMS value. We said it's very important to write the sinusoidal source in terms of the RMS value, especially when you do power calculations, because the RMS value is the value that's going to give you the same power as the DC, as an equivalent DC source. Then all of a sudden we kind of like moved and discussed complex numbers. And the reason for discussing complex number will become obvious in this lecture. So we said, in general, we use kind of like all what we dealt with was kind of like real numbers. Now we're going to discuss complex numbers. And the complex number has 2 parts or 2 portions. The first one is the real part, and the second one is the imaginary part. We have J here in front of the imaginary part, and J is square root of -1. Again, here in electrical engineering, we actually use J instead of I, because I is usually reserved for current. It turns out there are two representations. The first one is the rectangular form, or the Cartesian form representation, and the second one is the polar form. So to move between these two representations, C is the amplitude, is going to be the square root of A squared plus B squared. Theta is the inverse tangent of the imaginary part over the real part. And if you recall from last time, we studied various properties of complex numbers. I'm not going to review them in this lecture. Any questions? So let's go back to circuits. So previously we studied math, and this now let's go back to circuits. So in any circuit analysis, we have a voltage, resistance, or voltage and circuit element, a voltage source or circuit element, and we're trying to find the voltage, either the voltage or the current. So let's assume that we have a source that's we have a sinusoidal source, Vs, and Vs is given by Vn cosine omega t plus phi, and this Vs is connected to a series R under circuits. So we have a resistor, we have an inductor, and we are asked to find the current immediately after the switch is open and the switch is closed. So the general way of solving this problem is actually to apply KVL. So if we apply KVL, we're going to get minus Vs plus the voltage across the resistor plus the voltage across the inductor equals to 0. So in this case, the Vs is Vm cosine omega t. The voltage across the resistor is the current I multiplied by R, and the voltage across the inductor is actually the derivative of the current multiplied by the inductance. Okay, that's something that we are all familiar. The issue here becomes rather complicated when we try to find the expression for the current. So if you recall, if we have a DC source, then we know that the expression for the current, if Vs is DC, then the current I is going to be I final plus I initial minus I final e to the power minus t divided by tau. Tau here is L divided by R. We need to find the final value, the initial value of the current, and we can actually find the expression for the current. But the main problem here is the source is not a DC. The source is an AC source, a sinusoidal source. So it turns out, without deep dive into details, this is something that you're going to cover in Math 208, is that the current has two portions, has this portion and another portion here. So let's look into the first term here. So the first term is called the transient term. Why we call it transient term? Because this term will appear for a very short period of time, then it will die, because we have an exponential term here. So if you recall in chapter 7, that's the term that we care about, because we want to study the temporary behavior, or the short time or the short-term behavior of the voltage and the current across the capacitor or the inductor. But if we have a sinusoidal source, we are more interested in studying this steady state, something that be sustainable forever. And this term, the second one, is the steady state term. So let's observe what we have in here. So if you recall, the voltage source is of sinusoidal nature. The current here, the steady state current, has a sinusoidal nature. It's also sinusoidal. The important thing is actually here, the two or three major observations. So the first one is we have sinusoidal. The second one is frequency does not change. So the frequency here is the same as the frequency of the source. Nothing has changed, the frequency. However, the third thing is phase changes. So the phase actually, it used to be just phi, now it's phi minus theta. And I said T should be 4 also. Amplitude change. So the amplitude used to be Vm. Now the amplitude is Vm divided by square root of R squared divided by omega L squared. So there are two things that are not changing and two things that are changing. So the two things that are constant or they are fixed is that the steady state current is actually of sinusoidal nature. The frequency does not change. The two things that are changing is the first one is the amplitude. The amplitude is changing. The second one is the phase. The phase is also changing. And this is only true for steady state term. So let's find the steady state inductor voltage. Let's find the voltage across the inductor, the steady state voltage across the inductor. So if we do that, we can apply the formula di by dt. So we're going to get L. If I differentiate this one, I'm going to get L multiplied by omega Vm. Negative sign because the derivative of cosine is negative sign. So if I write everything in terms of cosine, I'm going to get where I use the fact that if I have cosine alpha minus beta, it's going to be cosine alpha cosine beta plus sine alpha sine beta. So you can choose beta to be 90 degrees or negative 90 degrees. So in this case, you're going to get negative sine alpha. Okay. So what do we notice here? We notice also that we have sinusoidal voltage. The frequency does not change. The phase changes, however, the amplitude changes. So again, it seems that every quantity that we have we still have a sinusoidal voltage or sinusoidal current. The frequency does not change, only the amplitude and the phase. So what do you think the logical way of dealing with such a circuit? So let's say that, well, why would they complicate things? Why would they care about things that are fixed? I know, like, I know that the amplitude, I know that the frequency is going to be fixed. It's going to be sinusoidal anywhere. So it's no big deal here. So why would they add them? If I add them, then I'm going to complicate things. So let me just focus on things that are changing. Let me just focus on the phase and the amplitude. And in order to do that, I need to introduce some notion of transfer, some notion of transformation. It's called Phasor transfer. So what do we mean by, first of all, before studying Phasor transfer, let's define transform. What do we mean by transform? So a transform, it's kind of like a change of, it's not entirely correct, but transform is a change of the function representation. So I'm representing this function with sinusoidal or with a sinusoidal representation. It's called the time domain representation. So let me represent it with something that does not have the time element here, something that's independent of time, and this is called the Phasor transformation. It's much like if you have a complex number, you can write it as ZA plus JB. And in this representation, you have access to the real and the imaginary part, or you can write it in polar form, where you have the amplitude and the phase between the imaginary and the real part. So this representation is going to give you information about the real and imaginary part. This representation is going to give you a direct information about the amplitude and the phase between the real and imaginary part. Okay, so you will see that very often when you deal with functions, with especially time domain functions, that you're going to change the representation. You move from one domain to another, and this movement is going to simplify, can either simplify your calculations, or it can allow you to have direct access to hidden information about the function. Much like this representation, you can see here, just looking into this, the Cartesian form of a complex number, I can directly have access to the real and imaginary parts. But it's not straightforward. It's not like directly. I have to do some calculations to get the amplitude. I have to do some calculations to get the phase difference between the imaginary and real parts. Similarly here, for the polar form, the phase representation is actually there. I can find the phase between the imaginary and the real part. The angle or the amplitude is actually, the amplitude is, I can easily define, or can easily find the amplitude here. But if I ask you to find the real and the imaginary part, then you need to do extra step here. You need to do extra calculation. So you need to take the cosine of the angle, multiply it by c. You need to take the sine of the angle, multiply it by c, and this will give you, the first one will give you the real part, the second one will give you the imaginary part. So this is not entirely transformation. This is just a change of representation, but this is going to give you like an idea of what we're expecting here. So for each transformation, there is a forward transform. So you're moving from one domain to another, and there's a backward transform. You're moving from, you go back to the original domain. And in this course, the multiple transforms, you see in E207 and in E207 you will be introduced to another transform. One is called Laplace transform, and the other one is called Fourier transform. But the very first transform that you're going to be introduced to in electrical engineering is actually Phasor transfer. So any questions about? Okay. Yes, Karim.
Doctor, I have a question about the steady state.
Yes.
So let's say that I have a circuit. The steady state is like the current that like will happen after a certain amount of time. Like
the steady state is the current that's going to be steady. It's going to be there forever. So I think about it this way. If you open a door and close it, the door is open and close it, then you see there's some sort of like oscillation here. That's called the transient behavior. And it's going to be there for a few seconds, right? If you observe it here, you're going to see that for a few seconds, right? معي بكريم.
أيوة معك دكتور.
Okay. I mean, you have to unmute yourself when you ask questions. So the steady state is the state that's going to happen after this oscillation, which is in this case the door will be closed, will be completely closed. There's no oscillation anymore. So think about it this way: you have a sinusoidal source, then you close the switch. There's some currents that's going to appear, and there's another current at the same time that's going to stay forever. And the steady state current is the current that's going to stay. That's going to stay forever. In our case, for example, if we go to the DC case here, if we have a DC source, then the current, the steady, then you see that the steady state or the transient current is the change in the current that happens when you open or close the switch. When you close the switch. And the steady current is going to be Vs divided by R, the current that's going to stay forever.
Okay, thank you.
Okay, going back to the transform. So let's see what we can, why we are introducing Phasor transform. Why I'm saying this? Why I'm talking about, well, we need a transform to study steady state current or steady state circuits or steady state sinusoidal sources. So first of all, let me just introduce the Phasor transform. So we noticed that if you have a cosine, I'm using the general form here, then you know that the real part of it is going to be cosine omega t minus the imaginary part is going to be okay. So the real part will be the cosine, the imaginary part will be the sine. If I take this function, what I mean by this representation, it doesn't matter whether it's a sine or cosine, because a sine and cosine, the difference between them is a 90-degree shift. and apply it to a system, the output will be something like this. So you can see that the frequency does not change, the phase has changed, and the amplitude has changed. So that's basically what we did. We took our input to the circuit as a sinusoidal source. We saw that the output, say like the steady state current, is going to have the same frequency, different amplitude, and different phase. And that's basically what I'm doing here. So I'm taking this A multiplied by e to the power j omega t plus b, input it to a system. The output will be a sinusoidal with the same frequency, but different amplitude and phase. It turns out that this system is called LTI system. You'll study it in 807, linear time invariant system. And if we have such a system, then we can apply the Phasor transform. So, but first of all, let's define Phasor. So Phasor is a complex number that carries the amplitude and the phase angle information of a sinusoidal function. So that's why we introduce complex numbers in the previous lecture. We introduced complex numbers because we're going to use Phasor transform. And what do we mean by Phasor transform? Let's start with what do we mean by Phasor? Phasor is actually a complex number that captures the things that are changing, the amplitude and phase angle of sinusoidal function. We saw that if we input a sinusoidal function, the output will be a sinusoidal function with the same frequency but different amplitude and phase. And instead of caring about everything in the system, let's care about things that are changing. And we need a phasor representation, which is a complex number-based representation to capture the things that are changing. Okay, very good. So Phasor transform, this is the definition of Phasor. Phasor transform, you're taking sinusoidal input and you're extracting the components that are changing, and you you put them in a complex domain-based representation. So this P stands for Phasor transform. So you take this function, then you discard the time and the angular frequency. You only end up with the amplitude and phase. You can use either representation for that. So let's derive it. Okay, that's what we know from last time. We know that cosine of theta is going to be the real part of the complex exponent here. And sine of theta is actually the real part or the imaginary part of the complex exponent. Okay, that's reasonable. So let's take this source, Vm cosine omega t, and manipulate it in a way to just find a representation that captures the amplitude and phase. So I know from this one that cosine of omega of an angle is actually equal to the, it's equivalent to the real part of this complex exponent. Okay. So by the property of exponents, I can write it as the following. I can move Vm inside. And change the order of the representation. And that's what I get. So this representation, this is the Phasor transfer of this function. So if you recall, we said that for every transform we have an inverse transform. So the Phasor transform is called the frequency domain representation. And this representation is called the time domain. So if you give me the frequency domain, can I go back to the time domain? Turns out that there is a way of going back, and this is called the inverse Phasor transform. We're going to use cosine convention. We'll come back to it. We'll see that in one of the exercises. So the inverse transform, if I'm giving you something in a complex exponent, then I'm asking you to write the time domain representation of that. You will take, first of all, this one stands for the inverse transform. You will multiply it by e to the power j omega t, and then you will take the real part of it, and this, in this case, you will end up with Vm cosine omega t plus v. Do you have any question? You seem awfully quiet.
I mean, to me, I get the questions when we start solving. I think I need to understand more.
Okay. طيب. Okay, let's see what we can do with this circuit here. This is a circuit that we studied. We said that the current will be given by this very long formula. I don't know if you can see it here, but let's apply the Phasor analysis to that. So let's study the steady state current here. We don't care about the transient behavior. So the steady state I can write it in this form. Im and if you remember that I have the voltage sources Vm cosine omega t plus v. So what is the Phasor transform of that source? Is going to be Vm, or I can write it as so now from KVL we know that so if we care about the steady state current, then L multiplied by the derivative of this with respect to time, you will see that it's going to be j omega multiplied by L multiplied by Im okay, plus R multiplied by the current, which is Im equals to the source, which is Vm okay. So that's basically what we did. So we took the expression, we assumed that the expression of the current, because we're talking about the steady state current, we assume that it's going to be sinusoidal with a specific amplitude Im and a specific phase beta, and we want to find what is Im with respect to the input and what is beta with respect to the input phase. So if we simplify it, and we note that the real of A plus the real of B is equal to the real of A plus B. So I can remove the real operator here. So let me remove the real operator here. I'm going to get j omega L Im equals to Vm okay. So now let me factor out the common terms here. E to the power j omega t is common among all of them. So if I do that, I will end up with Im is actually, if I take Im e to the power j omega t is going to be Vm e to the power a e to the power j v divided by r plus j omega. Okay. So what I need to do now is I need to take the right-hand side and express it as amplitude multiplied by phase. So in order to do that, I need to take the amplitude of the numerator, the amplitude of the denominator, and this is going to be equal to the amplitude of the Im, the amplitude of the current. I need to take the phase of the numerator and the phase of the denominator, and this is going to be subtracted, and this is going to be the phase of the current. Since the numerator is given to me in polar form, so I don't care. I mean, it's kind of like it's easier. So the denominator is the part that I need to be careful with. So if you're giving a real and imaginary part, then the amplitude of that is going to be square root of r squared plus omega squared L squared. So this is the amplitude. The phase is going to be the imaginary part. First of all, the phase is going to be the phase of the numerator minus the phase of the denominator, which is the imaginary part, divided by the real part. And this one is theta here. And if you go back to the original expression here, you see that this is the phase, which is V minus theta. And this is exactly the amplitude, which is Vm divided by R squared plus square root of R squared plus omega squared L squared. So it turns out there are two ways of actually solving this problem. The first one is actually by solving a differential equation in time domain. The second one is actually, well, all what I need to do is write the Phasor transform representation of every element in the circuit. Then just apply linear equations, things that we studied in Math 001. So is it clear, Shabab?
Clear. Yes, clear. Thanks.
Very good.
Doctor,
Yes.
I think in the left, in the second line from the bottom, there is an extra L there.
Oh, yes, yes. Okay. Now, I want to solve this exercise. Okay, let me start with exercise 2, then I'll go back to exercise 1. Exercise 2, exercise 3, then I'll go back to exercise. Okay. So in this exercise, we're asked to find the Phasor transform of each trigonometric function. So the first one is 170 cosine omega 377t minus 40. So the Phasor transform of this one is going to be complex. So I need to take the amplitude, which is 170, and the phase is minus 40. You see, it's very straightforward. Okay, for the second one, what will be the Phasor transform of this one? Ibrahim?
We should first change the sign to cosine.
Yes, exactly, because remember here we're using the cosine convention. So the very first step is to change the sign into cosine. So in order to do that, you need to subtract 90 degrees.
Then we can take the amplitude and the phase, and it will be straightforward as the first one.
Yes, exactly. It's going to be cosine 1000 t minus 70 degrees. And in this case, the Phasor transform will be 10 minus 70. Okay, very good.
So minus 90, Doctor.
No, minus 70. We have 20 minus 90. Okay.
Yes, yes, okay, that's
20 minus 90, and this is going to give me 70. Okay, the third one is asking us to use the Phasor transform to find the addition of 5 cosine omega t plus 10 cosine omega t minus 50. Okay, so first of all, let's find the Phasor transform. So what is the Phasor transform of the first term? Ziad?
5 and 36.
What's that?
7. Yes. For the
5.
first one.
5 and what?
36.87.
Yes. Okay. So the third one will be 36.87 degrees. What about the second term? Abdul Aziz Al-Hamdani?
10 minus 53.13.
10 minus 53.3. Okay, so now I can add them. So in order to add them, I need to write them in Cartesian form, or rectangular form. So this is the first term, this is the second term, so it's going to be 10 minus J5. And in polar form, this is going to be minus 20. 657. Okay. The fourth part is 300 cosine 20,000 pi of t plus 45 degrees minus 100 sine. So what should we do first? Abdullah Al-Tiriri.
First, we convert it to Phasor. We convert each term. Like the 100 sine, we turn it back into cosine, but put minus 90 degrees.
Yes, exactly. We put minus 90 degrees, so it's going to be minus 90. So here it's going to be minus 60, right?
Yes.
Okay, very good. Okay, so let me write down. Let me write this. So now we can apply Phasor transfer to every term. So here we have 300 45 degrees. Here we have 100, and the angle was negative 60 degrees. So the voltage is going to be 61.51 degrees. Okay, we showed that converting things into Phasor is very straightforward. So let's study, let's convert everything back to time domain. So let's do the inverse transform here. Yes, sir, question?
Yes, doctor, in the previous exercise, question 2. Can't we subtract 90 minus the angle, so it will be positive 70? Like 90 minus 20, I guess it will give us the same answer, if I'm not wrong. Like, for example, if we have sine 45.
Okay.
If we did cosine 90 minus 45, so we subtracted the angle from 90, we'll get the same answer. It is the same as adding subtracting 90 from the angle.
Okay, can you? You're saying that it's going to be 20?
Yeah, just put 90 in front, so 90 minus the 20. So it is something like 10 cosine 1000 t plus 70.
Okay, 90 minus 20.
Yes.
That's what you're saying. Okay. I see what you're saying here. First of all, in order to do that, you need to actually, because you're changing the phase here. Instead of 20, you're using negative 20.
Yeah.
Okay, so you're changing the phase. So probably the best way to think about it is in this way. So think about it as cosine of alpha minus 90, which is cosine alpha cosine 90 plus sine alpha sine 90. So this term is 0, cosine 90 is 0, sine 90 is 1, so it's going to be sine alpha. So that's why we subtract 90 here.
Yeah, but the same thing happens with the 90 minus 20. But I think it is better to not change the phase. Just
No. If you use 90 minus 20, then you need actually to take this one as a negative, which means this one will be negative as well, because sine is.
Yeah. Now this makes sense. Thank you.
Okay, let's find the inverse Phasor transform. So we're given things in phasors. Let's find. Let's write them in time domain. Walid?
Yes. We can write it 18.6 cosine omega t minus 54.
Exactly. Correct. Okay. This is going to be VT. For the second one, 5.
It will be 20 cosine omega t plus 45.
Okay. So first of all, let's simplify it, then do the conversion. So maybe first of all, let's simplify it. It's going to be.
And convert it into.
Yes. Okay. So now I wrote everything in polar form. So in this case, it's going to be 48.81 cosine omega t plus 126. Okay. The last thing is Mohammed.
We did the same thing, but with the second part only. We change
Yeah.
it, subtract, return it back to Phasor, then put it in the time domain.
Exactly. So if we do something like this, we're going to have. So the first part is given to us. It's written in Cartesian form. The second part is I need to write it in Cartesian form. It was in polar form. So this is going to be 28. So it's going to be minus. Okay. So we saw that applying phasor transfer is very straightforward. So let's go back to exercise 1. Exercise 1 shows a very interesting application of phasor transfer. So let's see what we have in here. So we are asked, we're given two functions, two sinusoidal functions, y1 and y2. We want to express y1 plus y2 as a single sinusoidal function. So the first way of doing this, we can use trigonometric identities. That's something that we are all familiar with. And that's something that we did in that you did actually in Math 001. So y1 is going to be 220 cosine omega t cosine 30 plus 20 sine omega t sine 30. Y2 will be 40 cosine omega t cosine 60 plus 40 cosine sine omega t sine 60. And y1 plus y2 is going to be, I can take cosine omega t as a common factor. I will get 20 cosine 30 degrees plus 40 cosine . Okay, so if I simplify it, I will end up with, substitute, I will end up with 37.32 cosine omega t minus 24.62 sine omega t. And remember, I was asked to express it as a single sinusoidal function. So this is equivalent to a cosine omega t plus phi. So my job here is to find a, to find a and phi. So in order to find a and phi, so I need to use Pythagorean theorem. So this one is 37 P2. This one is 24. This is A, this is phi. So A is going to be 37 P2 squared plus 24, 62 squared. And then A is going to be 44.72. Phi is going to be the inverse tangent of 24 . So it's going to be 33.43 degrees. Okay, so now I found A and phi, so I can write it as a single sinusoidal function. Okay, now let's see what we can do. How to solve this problem using Phasor concept. So if we use Phasor concept, we'll see that. Well, instead of doing that, so let me start by taking the Phasor transform of each one of them. What I'm saying here is that the first answer is 20. The Phasor transform of the first one is 20. The angle is negative 30. Or 17.32 minus J, 10. The second one is 40. The angle is 60, I believe. Yes, 60. It's going to be 20 plus J, 34, 64. So now if I add them, I need to add the real part with the real part, the imaginary part with the imaginary part. And in this case, I will end up with 37.32 plus J, 24.64. So Y will be in polar form is going to be 44. So if I use the inverse Phasor transform, I will end up with Y equals to 44.72 cosine omega t plus 33.43. So you can see here that, well, this problem is quite complicated when I solve it directly using trigonometric identities. But with the Phasor concept, I can transform everything back. I can transform everything into Phasor domain, then add the complex numbers, and then use the inverse Phasor transform to write things in time domain. Is this clear, Shabab? Ziad, question?
Yes, when we try to find y2 by trigonometric identity, shouldn't we use minus
Y2?
between the cosine and the sine? Yes, in the back, the previous slide. For y2, isn't it minus?
Or Y2? What do you mean by minus?
40 cosine and minus 40 sine.
40 cosine minus 40 sine?
For y2, the identity.
Oh, okay, yes, you're right. Okay, good, thanks. Okay, any other question, Shabab? Okay, we see how powerful using phasors, how powerful like Phasor transform in solving such problems. Okay, so far we haven't discussed or how to use Phasor transform in solving circuits. We kind of like briefly go over, kind of like briefly went over applying KVL in order to solve the circuit, but we're not there yet. So what we need to do is, after all, what we need to do is actually solving for the voltage and the current in any part of the circuit. So if we want to solve for the voltage and the current using Phasor transfer, then two things are required. The first one is we need to establish a relationship between the voltage, the Phasor voltage, and the Phasor current at the terminal of any passive circuit element. Say that you have a resistor, so you want to study the relation between the phasor, the voltage in the Phasor domain across the resistor, and the current in the Phasor domain passing through the resistor. And you use this relation to find one quantity from the other. Or if you have an inductor, then you need to find the voltage passing through the inductor, the voltage across the inductor in Phasor domain, and relate it to the current passing through the inductor in Phasor domain. So if we think about it in the time domain, when we talk about the voltage and the current, the voltage across the resistor and the current passing through the resistor, we're saying that they are related by Ohm's law. So if you know the resistance and you know the current, then you can find the voltage. Or if you know the resistance and you know the voltage, then you can find the current, simply by applying Ohm's law. If we have an inductor, on the other hand, then if you know the voltage, say like if you know the current and you know the inductance, then you can differentiate the current, multiply it by the inductance, and you'll get the voltage. If you know the voltage and you know the inductance, then you need to integrate the voltage to get the current. So we need to, and all of these analyses were done in the time domain. So what about the Phasor domain? How to relate the Phasor voltage to the Phasor current for the resistor, the capacitor, and the inductor. So that's the first thing that we need to develop. The second thing is we need to develop Phasor transfer or Phasor domain versions of Kirchhoff's and Ohm's law. So let's start with actually representing Phasor voltage, studying the relation between the Phasor voltage and the Phasor current. So we can define the notion of Phasor form of Ohm's law, saying that the voltage, the Phasor voltage, is related to the Phasor current by this quantity Z, and Z is called the impedance, and the impedance is a complex, in general complex. So if I give you the voltage across any circuit element, the Phasor voltage across any passive circuit element, then I need to know the impedance, something like the resistance, multiply it by, or divide the Phasor voltage by the impedance, and to get the current. So let's start with the resistor. So let's start with the time domain. So let's start with the time domain representation of the resistor. So we know the current Im equals IFT equals Im cosine omega t plus theta I. So if you apply the Phasor transform of the current, you will get Im e to the power j theta I. Then the voltage across the resistor, we can use Ohm's law. The voltage will be the resistance multiplied by the current, no matter what type of the current we have. So the voltage is going to be R multiplied by I. Applying the Phasor transform of the voltage, you will get R multiplied by Im, or the Phasor voltage, again here is the current, the Phasor voltage multiplied by the Phasor current is the Phasor voltage, and the Phasor current is related by the impedance here, which is the resistance. So the impedance, remember, in all of the analysis here, we need to find Z. It turns out for the resistance, Z is actually equal to the resistance itself. So the fact that Z is real implies that the voltage and the current, they are in phase. Which means that if you plot the voltage, the time domain representation of the voltage, you plot the time domain representation of the current, you will see that they are in phase. They are on top of one another. There is no shift. Okay, so what about an inductor here? So for the inductor, the current of the inductor is given by Im cosine omega t plus theta plus Vi, theta I. Then the Phasor transform of the inductor is the same as the Phasor transform of the current bicycle of the inductor is given by this formula. So let's find the voltage. So pay attention here. So our ultimate goal is to find Z here, or resistor, inductor, and capacitor. We know that for resistor is equal to the resistance. So let's see what Z for the inductor. So the voltage is going to be L di by dt. So if I write everything into, if I use cosine convention, it's going to be Im I think I'm missing. Yes, here there's a negative side. Cosine omega t plus theta I minus 90. So V so let me just move omega here. So if I apply Phasor transfer, this one I will get so e to the power j90, negative j90 is negative j. So you will get so remember this is the current, the Phasor current. So in this case we have the impedance of the inductor is j omega L, and the voltage can be written as omega So you can see that Z for the inductor, the impedance of the inductor is complex. The first one is complex. Is given by j omega multiplied by L. The frequency, the angular frequency multiplied by the inductance. Okay, we can see here that because this one is complex, the result is that the voltage and the current, they are not in phase. They are actually 90 degrees out of phase. So if we consider the situation when t greater than or equals to 0, the voltage, this is the voltage, the black curve, the voltage reaches its minimum value before the current. The current is the blue curve. So meaning that the voltage is leading the current, or the current is lagging the voltage. So this shift, this 90-degree phase shift, corresponds to the period divided by 4, which is fourth portion of the period. Any questions, Shabab? I have to stop here. Right.
Could you just go to the previous slide? I didn't get how e to the power negative j90 is equal to negative j.
Okay. Do you agree with me on this?
Yes.
Okay. So this one is 0.
Okay.
This one is 1.
I got it now.
It's very good. Any other questions, Shabab? Ziad?
In the final form, why did we add the 90 degree? Is it to correct the lag?
This one?
Yes.
No. It's kind of like okay, V equals to J omega L multiplied by I, right?
Yes.
Okay. So if I use a polar form, I will get omega L 90 I, which is in this case Im theta I, right?
Oh, okay.
So multiply the amplitude and the phase.
Yes, thank you.
Okay, good. Any other questions, Shabab? Okay. Mohammed?
Yes, sorry, Doctor. In the following quiz, is it okay if you use the final formula sheet or not?
The next quiz?
Yes.
I'm not sure. Okay, yeah, we can use the final. Well, yes, we can use it.
Okay, thank you.
Doctor,
Yes.
I think in the formula sheet the value of alpha for a series connection is wrong.
I will double check it.
Okay.